All right, let's talk about making your software faster. To do that, you really have to get into concurrent programming. But where do you even start? Well, the very first step, the absolute foundation, is something called decomposition. It's basically the art of taking a huge problem and smashing it into smaller pieces that your computer can work on all at once. So let's dive in. Okay, so picture this, and I think we've all been there. Your app is running slow. It's sluggish, and worse, your users are starting to complain. Now, you could just throw more hardware at the problem, but that's not always the best way. The smarter way is to get your program to do multiple things at the same time. The real question is, how? How do you actually pull that off?
The secret? It's all about a mental shift. You kind of have to rewire your brain. From the time we start coding, we're taught to think in a straight line. Do this, then do that, then do the next thing. But to really tap into the power of concurrency, you've got to break out of that sequential mindset. You have to start seeing the parallel paths hiding in your code.
And that right there is the million-dollar question, isn't it? It's one thing to say, oh, just think in parallel. But it's a whole other challenge to look at a single, tangled problem and figure out how to slice it up into neat little tasks that can run at the same time and, without tripping over each other and causing chaos.
Well, this whole process has a name. It's called decomposition, and it's really part art, part science. It's all about hunting for the parts of your problem that are genuinely independent. You can think of it like being a detective, searching for these hidden chances to get more work done in the same amount of time.
So if we want to get a little more specific, decomposition is just the process of breaking a problem down into smaller, self-contained tasks. The whole point, the end game, is to find these chunks of work that don't need each other to get done. Because once you have those, you can toss them to different processor cores and let them all run at the exact same time.
Okay, so where do you start? First things first, you have to play detective and figure out the dependencies. You need to map out which tasks rely on other tasks to be finished. And to make this super clear, let's use a really simple everyday example, making a pot of chicken soup.
A really good trick here is to actually work backward from your final product. So our goal is the finished soup. What needs to happen right before that? We have to simmer all the ingredients together. Okay, and what needs to happen before we can simmer? Well, we need the broth, and we need all our veggies, the carrots, celery, onions, all chopped up. See, each of those is its own little task.
And here it is. This is the aha moment. If you look at our little plan, you'll see there's no dependency between making the broth and chopping the vegetables. They're totally independent. That means you could have one person working on the broth while, at the exact same time, other people are chopping the carrots, the celery, and the onions. Boom! That's our opportunity. That's where we can use concurrency.
Right, so once you spot these opportunities, there are really two main paths you can take. The first is called task decomposition. This is all about splitting up the work itself. The analogy here is perfect. Imagine clearing a snowy driveway. One person shovels the snow and another person follows behind scattering salt. They're doing two different tasks to achieve the same goal. Then you have data decomposition. This is about splitting up the data. So now, instead of one shoveler, you have two people, each with their own shovel, and each one clears a different half of the driveway. See the difference? Same task, but they're working on different chunks of data.
Okay, let's dig into that first one a bit more. Task decomposition. This is where our focus is squarely on dividing up the actual jobs or functions of our program.
Probably the most common pattern you'll see here is the pipeline. I mean, the name says it all, right? Just think of a factory assembly line. Each station or worker does one very specific thing and then passes the product down the line to the next person. It's the exact same idea in software. Each stage in our pipeline is a task that chews on some data, does its thing, and then passes the result on to the next stage.
And the absolute classic example for this is doing laundry. Think about it. First, you put load number 1 into the washer. Simple enough. But here's where the magic happens. As soon as that first load moves into the dryer, what happens to the washer? It's free, so you can immediately put load number 2 in. A little while later, you've got load 1 being folded, load 2 is in the dryer, and load 3 is just starting in the washer. You've got 3 things happening at once. All your resources, the washer, the dryer, the folder, are busy, and you're getting through that pile of laundry so much faster.
Now, what does this look like in code? Well, you might set up independent worker threads for each one of those stages. So here, we're literally starting up separate threads for a washer, a dryer, and a folder. Each one is its own little worker, just waiting for a job to show up. It grabs the work, processes it, and then passes the finished product to the next stage in the line. Just like the real laundry example. This keeps all our parts moving and gets the job done as efficiently as possible.
All right, let's switch gears now and talk about that second major strategy, data decomposition. Remember, this time we're not splitting up the jobs, we're splitting up the data we're working on.
The most straightforward pattern here is something called map. The idea is super simple. You take one single operation, or a function, and you apply it to every single item in a huge collection. A great example is if you wanted to convert a whole folder of photos to black and white. Converting one photo has absolutely no effect on converting any of the others. They're completely independent. This is what we call an embarrassingly parallel problem, and it's perfect for this map pattern.
And the speed up you can get from this, it can be absolutely mind-blowing. Just look at this chart. It shows a simple file search. Doing it the old-fashioned sequential way, one file after another, takes 3/4 of a second. But when we use a concurrent map pattern to search a bunch of files all at once, that time drops to less than 5/100ths of a second. That is a massive difference, like a 15x speedup. It's just incredible. Now, a slightly more advanced pattern for data decomposition is called fork/join. You can think of it like a two-step dance. First, you have the fork step. This is where you take one giant task and you break it apart into a bunch of smaller, identical subtasks. Then once all those little tasks have been finished in parallel, you move to the join step, which is where you scope up all the individual results and stitch them back together into one final answer.
Let's use an analogy. Imagine you're tasked with counting a mountain of election ballots. The fork step is when you split that huge mountain into, say, 4 smaller, more manageable piles. The process step is when you hand each of those piles to a different person to count at the same time. And finally, the join step is when you take the 4 separate totals from your counters and add them all up to get the final grand total. It's a classic divide and conquer approach.
And the code really reflects this logic perfectly. The fork part, that happens when we use a thread pool and its map function. We're basically telling it, hey, take this process pile function and run it on every single one of the vote piles. The thread pool handles distributing all that work across a bunch of threads for us. Then the map function conveniently waits for all those workers to finish. The join part is that simple loop at the end where we iterate through all the partial results, the worker summaries, and combine them to get our final answer.
Okay, so we know how to split things up now, by task or by data. But that leads to a really important question. Just how small should we make the pieces? And this idea has a name. It's called granularity. And this is a total balancing act. If you slice your tasks up too small, we call that fine-grained. You can actually slow things down because of all the overhead of just managing those zillions of tiny little tasks. But if you go the other way and make the tasks too big or coarse-grained, you run a different risk. You might have one processor core getting stuck with a giant task that takes forever, while all the other cores finish their work early and are just sitting around twiddling their thumbs. What you're looking for is that Goldilocks zone, that sweet spot right in the middle.
Okay, we've covered a lot of ground, so let's wrap all this up into a nice, practical toolkit that you can actually use when you're looking at your own code. So here's your cheat sheet. If you need to split up the work, you're looking at task decomposition, and your go-to tool is the pipeline pattern. It's fantastic for anything that feels like an assembly line. If you need to split up the data, you're using data decomposition. For those simple cases where you're doing one thing to many items, the map pattern is your best friend. And for those more complex, divide and conquer type problems, you'll want to reach for the fork/join pattern.
So we've gone through the theory, we've looked at the patterns. The only thing left to do is actually put it into practice. So I'm going to leave you with one final question to think about. Go look at the code you write every single day. Now that you know these patterns, now that you know what to look for, where's that hidden opportunity? Where can you stop thinking in a straight line and finally start working in parallel?